Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. Today we will talk about solubility, drug solubility. This is a very important parameter because most of the drugs are taken orally and they have to be water soluble. But then as a drug reaches the GI tract, goes to the stomach, intestine, the pH in the stomach is extremely low, a value of 2, and then it rises to a value of 4. Okay. So, the drug has to be soluble at all these pH conditions. Okay. Once that is done, the drug goes into the bloodstream where the pH is 7.4, again the drug has to be soluble. Okay. So, drug has to be soluble at all these conditions, and hence solubility plays a very important role in determining its bioavailability, efficacy, dosing strategy, and so many parameters. Okay. So, what is the definition of solubility? It is the maximum dissolved concentration in a solvent at a given condition, that means temperature and so on. Okay, so, it determines the intestinal absorption. So, if the drug is not soluble, it remains as a solid, so it may get effluxed out from the through the GI tract, and it also determines the oral bioavailability, because whatever goes inside has to come on the other side to the target site, hence the oral bioavailability is also determined by the drug solubility. So, poor absorption and poor bioavailability are big problems because of poor solubility. Insufficient solubility in IV, because when the drug is given intravenous, it cannot be in a solid form, it has to be completely dissolved. It will exhibit low activity because solubility is low. So, whereas in my lab it may work well, but when it goes through the GI, because of poor solubility, activity may look very low. The product development becomes a big issue. Okay. So, it becomes very expensive. How do I make the drug more soluble? So, we may have to think about a novel drug delivery system and so on. And then for the patient, it becomes a big issue, because patient has to take the drug quite often because the bioavailability is poor, the absorption is poor. So, for the patient also it is a big problem. So, solubility plays a very important role, that is the starting of the journey of the drug from the mouth or the oral cavity before it reaches the target site. Okay. So, let us look at this. Of course, you take a oral drug, it goes into the stomach, it has to completely dissolve here, and that is dissolution happens. That means aqueous solubility plays a very important role, and then it crosses the membrane, the lipid membrane, before it reaches the blood. So, whatever does not dissolve will slowly go down through the GI, and if it does not dissolve even at pH 4 and so on, it may get excreted. So, low solubility limits absorption and causes low oral bioavailability. And of course, solubility and permeability are opposed to each other, molecular properties, and good solubility is essential for intravenous dosing, because as I said before, when the drug is injected as an intravenous, it cannot be in a solid form, it has to be completely dissolved form. So, there are many parameters of the drug, or many structural properties of the drug, or structural features of the drug that determine solubility and permeability. Okay. Solubility is the first step, where the drug gets completely dissolved in the stomach fluid, and then it crosses the lipid barrier and permeabilizes and reaches the bloodstream. Okay. So, many parameters matter. So, we are going to look at some of them as we go along. The size matters. Okay. The shape matters. Okay. Size is also going to affect permeability, because very large molecular weight might not get permeabilized. Then the charge distribution on the molecule. Okay, so if the charge distribution, if it is very charged, of course it will be more polar, so it will be less lipophilic, it may not get permeabilized, but it may have good solubility, because charge, ionization, all these determine solubility. That is why solubility and permeability are sort of opposing. If I have a drug salt form, the drug is highly soluble, because as you know salts are highly soluble. But if it is a salt form, it may have polarity, so it may be difficult for the drug to cross the lipophilic membrane and reach the bloodstream. So obviously solubility and permeability are opposing each other here. So hydrogen bonding, ionization, charge, all these determine solubility, because if it is highly hydrogen bonded, then solubility is very poor. If it is ionized, of course solubility is good. If it is charged, also solubility is good. Melting point also determines the solubility, because melting point has relationship with crystallized form of the drug. If it is and so on, amorphous material is more soluble than crystallized material, so you sometimes try to make the drug more amorphous and so on actually. So solubility and permeability are sort of opposing each other, and we are going to see that in the next few lectures. Okay, solubility. You can do a lot of structural modifications to improve solubility. We can put in ionizable groups, okay. I can put in ionizable groups. As I said, salts are always highly soluble. That is why 70% of the drugs are in salt form. Reducing log P. Log P, we are going to spend more time in the subsequent slides. It determines the hydrophilic hydrophobic balance. So log P, if the log P is high, that means it is hydrophobic. If the log P is low, that means it is hydrophilic. That means higher hydrophobic, and lower it is hydrophilic, okay, hydrophilic, and so on. We will look at it in more detail later. Adding hydrogen bond donors and acceptors, okay, that is structural modifications, that is another thing we can do. Add polar groups, okay, that means we can have different types of oxygens, nitrogens there. We can have out of plane substitution to reduce crystal formation packing, because crystals, as you know, are packed structures, and highly crystalline materials are poorly soluble. So you break the crystallization by introducing out of plane substitution. Then reduce molecular weight. If the molecular weight is very small, the drug is soluble. Large molecular weight materials are not soluble. Salt forms increases dissolution rate. There is as I showed you last time, this particular software ADM, Swiss ADME predicts what is the solubility of structures. We can draw some structures, and then we can say this is the solubility of, it is a predictive tool using a certain regression relationship. Okay, we are going to look at some of these techniques by which structural modifications can improve solubility. Okay, let us look at this. Ionizable group. This is called artemisinin. This is a natural product. This treatment for malaria. It has got a very poor aqueous solubility. Okay, you can see a lot of hydrophobic groups, CH3, CH2, CH2, CH2. Of course, it has got some oxygen, but predominantly a lot of hydrophobic group. Okay, so what they do, they add a sodium salt here. So the solubility improves. It is a good aqueous solubility because of the sodium salt. This happens in Taxol. Taxol is an anti-cancer drug, and it has got extremely poor solubility and bioavailability. So when you make a salt formate, the solubility increases almost double. Now let us talk about log P. This is a very important thing which you will keep coming across. So I will spend some time on this. Log P is a ratio of octanol to water partition coefficient. So if you take a drug and take a mixture of octanol and water, drug will partition between octanol and water. Water is aqueous, so hydrophilic. Octanol is lipophilic, okay, hydrophobic. So if more drug is there in octanol, that means the drug is hydrophobic. If more drug is in water, that means it is hydrophilic. Okay, so the log P tells you the hydrophobic hydrophilic balance, okay, because octanol water, so hydrophobic philic balance. Hydrophilic water soluble or in blood soluble, hydrophobic, transport across the cell membrane. As you can see, log P is going to be contradicting between solubility and permeability. Okay, it's the log P is very high, that means it's hydrophobic, it will pass through the lipid membrane, but solubility can be poor. If the log P is low, that means it's hydrophilic, that means it will be highly water soluble, but passing through the membrane may be difficult. So, most of the drug like molecules will have a log P of 2 to 4. So, you take a balance, 2 is hydrophilic, 4 is hydrophobic, but it is neither too much of this or too much of that. Okay, that is the beauty of it. So, how do you estimate log P? You take logarithm and see a drug in octanol divided by drug in water. Okay. Again Swiss ADME, if you go to that software, we can draw structures and we can predict what will be the log P of a particular structure. Okay. So, if the log P is very low, below 2, then you may feel that it is going to be hydrophilic. So, it is better to reduce the hydrophilicity. If the log P is above 4, for example, some of the antifungal drugs have very high log P, they are highly hydrophobic, so you may have to think about making it more hydrophilic. So, generally if you have a molecule, you are testing it, and if you feel the log P is not in this range, so be careful, it may have poor solubility or bioavailability and so on. Okay. So, this equation is valid for unionized material, okay, unionized compounds. There is another term called log D, that is for ionized. Okay. It considers concentration in all forms, compounds in ionized form, compounds in unionized form, and so on actually. So, it takes in ionized and unionized. And of course, you will not find, suppose you have a solvent, you might have very little or practically 0 ionized form, whereas in aqueous polar compounds, salts will get ionized. Okay. So, log P is a logarithm of drug in the octanol divided by logarithm of drug in the water, whereas log D you will take a drug in ionized in octanol, drug unionized in octanol divided by drug ionized in water, drug ionized unionized in water. As I said, if you have a solvent like chloroform, you are not going to have ionization. So, this term will become practically 0. So, you will have a drug in 2 forms, ionized and non-ionized, only in the aqueous form, but in the solvent you will not have that. So, this is called log P and this is called log D. There are different ways of calculating log P. There are many different softwares which calculate log P based on some regression relationship. So, you may get different answers depending upon the type of softwares you use. Okay. There will be a lot of difference because each software will select say 1000 compounds from the literature whose log P is known or experimentally determined, and then they will develop a regression relationship. So, if I use software 1 and software 2, I may get different values of log P. And some softwares use something called a group contribution method. That means a OH group contributes certain amount towards log P, more towards hydrophilic, whereas a CH3 group may contribute more towards hydrophobic. So, that is called a group contribution method. So, they calculate log P based on that. So, you get different values for log P depending upon the type of software we use, and similarly we get different values for log D depending upon the type of software we use. So, log P is the unionized form, whereas log D is the ionized form, and generally only in the aqueous we find the ionized and unionized, whereas if you take a solvent like chloroform you will not find the ionized form. So, you will have only one term in the numerator if you are calculating log D. So, experimentally how do I calculate log P? I take a mixture of octanol and water, okay, and then I put the drug inside and then I shake it nicely. Okay, I take a drug, octanol and water, then I shake it nicely and then I see how much of the drug is in the octanol layer, okay, how much of the drug in the water layer, and then I take a ratio, I take the logarithm. Okay. So, whatever amount of drug in the octanol we consider it to be hydrophobic, and whatever drug in the water layer we consider hydrophilic. So, that balance is called the log P. Okay, so, log P also plays a very important role, as I said, in the permeability or the diffusion. So, this is a data which was taken from this reference. Okay, so, we have to acknowledge this. So, as the log P increases, as I said, it becomes very hydrophobic. So, it is easy for it to penetrate the barrier. So, its diffusion or permeability is also very high. As the log P is very low, it is very hydrophilic. So, the permeability, that is its transport centimeter per second, is also logarithm of centimeter per second is also very, very low. So, they have drawn a sort of a linear relationship here. Okay, so, drugs which have very high log P will also have very high diffusion through that. Of course, this graph does not talk about solubility part, but it talks only about the permeability or the diffusion into that. Okay. So, log P, if I can alter log P to improve its solubility, okay, so make it more hydrophilic. For example, these are protease inhibitors, okay, these are called the protease inhibitors, and their R group is there on nitrogen. So, as you can see, different R groups: benzyl, oxycarbonyl, 8-quinolyl sulfonyl, 2,4-difluorophenylmethyl, 2-pyridyl-methyl. Okay. So, different R groups. So, log P keeps going down, as you can see, 4.67, 3.7, 3.69, 2.98, and the solubility has gone up tremendously, almost more than 700 times. You can see at 7.4, that is in the blood. This is Indinavir protease inhibitor. This is taken from this particular reference. It is very interesting. So, as we keep changing R group here and make it more hydrophilic or reduce log P from this value right down to this value, the solubility also increases, as you can see, from 0.001 microgram per ml and at plasma to 0.07. So, a big increase. So, altering log P or making it hydrophilic will improve. Of course, it may affect the permeability. We are not talking about that, but we are just looking at solubility. That is why in drug discovery, many parameters or features are going to be contradicting each other. It is not just you change one and achieve your goal. When you change one and make it favorable, something else could become unfavorable, as you can see in this particular example. The log P decreases, so the solubility increases, but we do not know about the permeability of this particular change. Okay. Hydrogen bond donors and acceptors. By adding hydrogen bond donors and acceptors, we can change the aqueous solubility. For example, what is a hydrogen bond donor or acceptor? Oxygen, nitrogen are defined as hydrogen bond acceptors, okay, whereas NH or OH groups are considered as hydrogen bond donors. Of course, in acidic OH will become O minus and H plus, then that is not an hydrogen bond donor, please remember that. But if you take water in this particular example, okay, water is there, you have the oxygen, hydrogen, hydrogen. So, the oxygen here becomes an acceptor, whereas these OH and OH they become donor actually. So, it has got three things happening, it is accepting as well as donating. So, you look at this drug, this is an anti-AIDS drug, and there is an R group here. R is camphonyl, it has got poor aqueous solubility, poor bioavailability. So, introduction of OH here, look at this, we are introduced OH. So, what happens? It can have an hydrogen bond donor, okay, then aqueous solubility increases, the bioavailability also increases, very interesting. Again, this was taken from this particular reference. Look at these drugs, these are all antifungal drugs. As originally I said, antifungal drugs always have poor solubility. Look at this, this is called a polyene macrolide, it is a huge structure. So, it is called a macrolide, the solubility is 0.11 milligram per ml. As we can see here, the solubility is 291 milligram per ml. Okay. And then look at this, solubility has become 377 milligrams per ml. Add polar groups. Okay. So, we can add polar groups, that means we can add oxygens and nitrogens. Look at this molecule, it's got 1 oxygen, 2 nitrogens, okay, 3, solubility is 0.62. Now they have added oxygens here and here, solubility becomes 1.69. Look at this molecule, okay, some of the CH2 groups have been removed, solubility has become 1.66. Now make an acid out of this, solubility has gone to 7. So, we have almost increased the solubility by 10 times here. Log P here is 2.12, here it is 0.22, because we have added, we have removed lot of CH2 groups which are hydrophobic, that is why log P has gone down. So, log P has gone down, solubility has increased, so we have added more polar groups. Out of plane substitution, if a structure is well packed, very crystalline, solubility is very poor. Look at this structure, this is it is in a plane, single plane, you have because we have the fused rings, so they will be planar, planar, planar like this, so it is highly crystalline in nature, so the solubility is extremely poor. Planar molecule, they are stacked. This is a AMPA glycine N receptor antagonist. Now all you do is you add a acetyl group here. So what happens, no more it is a plane, because of this what happens, the molecule is not a flat structure, but it has got structure like this. Okay. So because of the acetyl groups, the molecule is like this, so it become non-planar, so solubility is become little amorphous, so solubility has increased to 150 microgram, so big increase, that is called out of plane. So any crystalline material, if you make it into amorphous material, solubility is increased. This is one way of structural modification. Sometimes they add another material which prevents the crystallization of the parent compound, the drug, so that it becomes amorphous. There are many examples where when we make the formulation of the drug, they add another compound which will prevent the crystallization and hence the formation of crystal structure. Okay. So again the log P, there is a difference in this minus 5.93 to 4.51. Okay. So factors, physical state of the compound, okay, solid, amorphous, crystalline, polymorphic. So more amorphous it is going to be more soluble, pre-dissolved in solvent. So if it is in a liquid form, composition and physical conditions of solvent, type of solvents. Sometimes they add also co-solvents to improve solubility, especially in IV formulation, salts, ions, proteins, lipids, surfactants. Surfactants can also make it more soluble. pH, modify the pH conditions to make it soluble. Temperature, I can change the temperature. Of course, when we talk about a oral drug, we will not be able to talk about changing temperature. Okay. Okay, so there are many tools for measuring solubility. One is called the equilibration time, that is time taken for dissolved and undissolved form to reach equilibrium. So what I do is I take a solid drug, put it in the solvent or water, and then I will see how long it takes for it to reach equilibrium for the solid and the dissolved form. Then separate solid and estimate amount dissolved, okay, by using a filter paper or a centrifuge. I can use detect how much has been dissolved using ultraviolet, mass spec, turbidity. These are some methods which are approved by FDA for determining solubility, and all these are very, very important. Not only the amount that is dissolved, but also how long it takes for the material to dissolve. Okay. So we looked at many structural properties, lipophilicity, which affects solubility. So, lipophilicity is determined by van der Waals, dipolar hydrogen bonds, ionic interaction, size, molecular weights, shape, pKa. pKa is nothing but dissociation constant. pKa is also determined by the functional group, what type of ionizable group proper, crystal energy, that is crystal stacking, melting point, all these also affect the solubility. Okay, let us look at the kinetics and thermodynamic solubility. What is this kinetic solubility? The compound is fully dissolved in an organic solvent, then added to aqueous buffer. Equilibrium is not reached between the dissolved compound and the solid compound. Okay, this is called the kinetic solubility. That means you dissolve it completely and then you are then taking it into another solvent, so the solubility changes. Okay. Thermodynamic, the addition of an aqueous solvent directly to solid crystalline material and then establishment of equilibrium between dissolved and solid material. This is thermodynamic solubility, other is kinetic solubility. Thermodynamic solubility is the reaching of equilibrium between the dissolved and the undissolved, whereas in kinetic it is in a dissolved form, okay, then you transfer it into another solvent. So, equilibration is not reached between this dissolved compound and the solid compound, okay, and that is what is called kinetic solubility. Okay. For example, I take a drug orally and the drug goes to the stomach and then the stomach empties. So, the time is fixed, within that time the drug has to dissolve, that is why kinetic solubility plays an important role. Thermodynamic solubility is the if the drug remains in the stomach for a very long time without the problem of the emptying of the stomach contents, then it will always reach an equilibrium, that is called a thermodynamic stability, that is the ultimate solubility. So, physiology and on solubility. The gastrointestinal tract is a dynamic environment because food comes in, water comes in, and then after a certain time the enzymes play an important role and then there is an emptying. So, physiology of the intestinal tract, species differences in gastrointestinal tract, that means one person may have different set of bacteria, another person may have a different set of bacteria. Food, what type of food we are eating, all these also play a very important role. Of course, we do not have much control, but as a medicinal chemist we do not have much control on this, but these also matter a lot. Okay. So, if you look at the physiology of the gastrointestinal tract, this was taken from a public domain. Okay, we have the stomach, then we have this is the colon, this is called the duodenum, okay, this is called the jejunum, okay, then this is called the ileum. Okay, so the food esophagus, then stomach, then duodenum, then it comes to jejunum and then colon, descending colon and so on actually. Now, the surface area of each of these regions are very different, the pH of each of these regions are very different, and the pH changes depending upon whether food is available inside or not. Okay. So, for example, if you look at the esophagus and stomach, transit time in esophagus could be very fast, 30 minutes, then goes to 3.5 hours. The surface area is 0.1 meter square, pH is very low, 1.4 to 2, and when it is fully fed it could go up to 3 to 7. Now, if you look at jejunum here, that is we call it small intestine, 3 to 4 hours. Look at the surface area, tremendous, 120 meter square, and then a pH is higher, 4.4, 6.6, and then fed 5.2, 6.2. If you look at the ileum here, pH is 6.8 to 8. Okay. So, the surface area of the small intestine jejunum is very large. So, we can expect lot of drug absorption in this region when compared to say stomach, and pH is also very low in the stomach. Now, if you go to colon, the transit time is 1 to 3 days, the surface area is 0.3 meter square, it has gone down tremendously, pH is also high, 5 to 8. Okay. So, each of these regions are very different, the transit times are very different, the pH conditions are different, and if you see the stomach pH can change from very acidic to almost higher values depending upon whether it is fasted or unfasted. So, the drug absorption can be very different in each region. So, if I want a fast acting drug, I want it to dissolve say in stomach. If I want a normal drug, I want it to dissolve in the small intestine. So, the drug absorption can change, the drug action can change, and so on actually. So, we need to understand the physiology of the stomach to understand the solubility and hence drug action. So, physiology of the gastrointestinal, GI has a pH gradient throughout its length, as you can see starting from 1 right up to 5, 6. Acidic pH at the stomach, acidic neutral in the small intestine, basic in the colon. This wide range of pH, long transit time, high surface area of small intestine. So, most of the drug should get higher absorption of drugs than in the stomach and colon. Acidic and basic drugs have different solubilities through the GI tract. As you can see, acidic drugs, that is pKa is acidic, basic drugs pKa is basic. So, they will have different solubilities in the stomach. Bases are more soluble in the stomach and upper small intestine due to ionization at acidic pH. So, if the drug gets ionized, it will not go through the lipid because they are very polar. If the bases will not get ionized, so it will travel through. So, bases are more soluble in the stomach. Acids are more soluble in the later section of the small intestine because of the region is more basic. Okay. So, GI tract as pH can be different among species. Rats and humans are good acid secretors, cats and dogs secrete less acid. So, if the drug solubility is pH dependent, differences in solubility between species will result in different absorption. So, rat you will get pH changes. So, the gastric emptying time is 10 minutes, rabbit 30 minutes, dogs 40 to 50 minutes, human 60 minutes. So, you see large difference. So, obviously, there could be differences in the performance of drug because of the emptying of the drug between various species, and when I am doing a clinical trial with animals, the results can get modified because the emptying times are also very different. Okay. So, we will continue on this solubility and drug permeability in the next class as well. Thank you very much for your time.